Hey everybody, it's Miss List, and we are here with Unit 6, and I teach 6.1 and 6.2 together because they're both relatively concise, and they give us a good introduction to what Unit 6 is going to be about. So 6.1 is on endothermic and exothermic processes, and 6.2 is on energy diagrams. The good news is that if this is your second chemistry class, so you may have had a first year chem class, the concepts of endothermic and exothermic and energy diagrams are usually covered in those classes. So hopefully this should not be new information to you. So when we talk about heat and thermal energy, it's always important that we define the system versus the surroundings. And I will say that this is one of the more challenging things for students to understand is what is the system and what is the surroundings. The system is the part of the world that you're studying. It might be a beaker, a chemical salt, water, or a thermometer, or it could be the salt that's dissolving. The surrounding is everything else except the system. It might be the air around, the tabletop, your hands holding the beaker. It might be the water in the beaker. So this is the trickiest part is defining this system versus surroundings concept. So in this picture, we have a beaker here. And when we talk about system versus surroundings, we can define these in terms of energy being absorbed by the system, and that would be considered to be endothermic. So the prefix endo means to go inside, like enter. So when reaction absorbs energy from the surroundings, this is considered to be endothermic. When a system releases energy to the surroundings, this is considered to be exothermic. And again, exo, exit, exoskeleton, those all mean outside. So when we think of our surroundings versus the system, energy is always being transferred between those two things. If energy is going into the system, then we give energy a positive sign. So that means it's going in. That's why you see over here in this diagram that heat and enthalpy both have a plus sign. And when energy is leaving the system, we give that a negative sign. So negative delta H and negative Q mean that heat is being released from the system. And again, this is always a transfer from the system to the surroundings or back and forth. And then these should be equal. So heat gained by the system should be equal to energy lost by the surroundings, or vice versa. And we can set those equal to each other. And sometimes in calculations, it's helpful to do this if we have calorimetry, which is something that we will talk about in this unit. This is where we measure heat being released from a substance, that would be our system, to the surroundings, and then we measure that energy. So endothermic processes is where heat or energy is absorbed by the system from the surroundings. And we give this a positive value. Products would have more energy than the reactants. So here on the left-hand side, we have this energy diagram. And in this energy diagram, it's showing a chemical reaction. We have the reactants on this side, and then we have the products on the right. And then the distance from the reactants to the top is the activation energy for this reaction. So that's the minimum amount of energy that's needed for this reaction to proceed. If reactants are down here and products are higher, that means I had to put energy in. Notice it's a net going up. So that means that energy had to be put into the system for this reaction to happen. This means that Q and delta H, so heat and enthalpy, would both be a positive value. And this is usually these energy diagrams we use to show chemical reactions. For phase changes, the phase changes that involve energy into a system are going to be melt, to boil or vaporize, and to sublime. All of those would be energy being put into the system or absorbed by the system. And then anything that requires a breaking or separation. So if I have to overcome IMFs, that's going to require energy. Or if I have to separate two ions from each other, that's the lattice energy. That's going to involve an endothermic process. Energy has to go in order to make that happen. On the opposite side, we have an exothermic process. Exo, aka exit, means that energy is being released from the system to the surroundings. And so that means that our Q and our delta H are going to be negative. And that's just to indicate that energy is leaving the system. If we compare this energy diagram, our reactants are higher than our products, and the energy has gone down. So that means that difference in energy had to be released to the surroundings. Any phase change where energy is leaving the system is going to be an exothermic process. So for phase changes, this is going to be any phase change where energy is being released to the surroundings. Things like freezing, condensation, and deposition all are going to release energy to the surroundings. I like to think about freezing is you have to take energy away from the system. That's why if you have like a fridge or a freezer at home, it is literally pumping heat out. And so that's why the area around that fridge usually gets warm. So that's one way that I remember this, is that it's got to get the energy out of the freezer. And the way they do that is by pumping it. This is going to be a exothermic process. I'm taking energy from the system and putting it outside the system. And then any change that involves combining materials. So combining materials would be like IMFs coming together, or maybe a bond being formed is going to release energy. When we have a solution formation, there are 3 steps that have to take place, and by combining all these processes, you can decide whether it's like overall endothermic or overall exothermic. And so in step 1 and 2, the solvent and solute must expand. Here in this diagram, we see the solute being broken apart. So anytime we're separating particles, that's going to take energy. And then same thing with our solvent is expanding. That's going to require energy. And then they will combine together. And when they combine together, remember that's an exothermic. And so by comparing how much energy it takes to separate the solvent and the solute versus them combining, we can determine whether it's going to be an exothermic solution or if it's going to be an endothermic solution. And that's literally just energy being released by dissolving, or energy being absorbed by dissolving. If I have an exothermic solution formation, that means when I mix the solute together, then my beaker is going to get hot because energy is being released from the system to the surroundings. If I have something that's an endothermic process, it's going to be absorbing energy from the surroundings. And so the beaker and area around it is going to get cold. This is one of the reasons why dissolving, sometimes people think of it as a chemical change, because there's this separation of particles and there's an energy change, a change in temperature. Some people think that it goes into the chemical change camp because of these things. On the other side of that coin is that usually chemical processes cannot be reversed without a lot of work. And we know that if we evaporate the solvent out, we can get our solute back. So you can see how this solution formation could fit into either category. The next thing we're going to do to introduce this unit is talk about enthalpy. And enthalpy is the difference in the energy of the products and the energy of the reactants in a reaction. And this is given the symbol delta H. And we always measure delta H by taking the products minus the reactants. This little Greek letter here, sigma, is for the sum. So if there's more than one product, we're going to add that together. And same thing here. If we have more than one reactant, we're going to add that together. Delta H is measured in kilojoules per mole. That might be different than our friend Q, because Q is often just measured in joules. Again, we want to make sure that we are paying attention to our labels, because that is something the College Board likes to see if you're paying attention. I mentioned this a second ago, but the activation is the energy that is needed to start the reaction. In our energy diagram, our activation energy is going to be the distance from the energy of the reactants to the top. That's the minimum amount of energy for the reaction to go. The lower the activation energy, so if I had a shorter distance to go up, maybe I just had this type of graph. If you lower the activation energy, the rate of the reaction is going to go faster. And then finally, a catalyst can lower the activation energy, but it will not change the delta H of the reaction. So that's something to keep in mind. Usually when we add catalyst, that's going to give it an alternative path. But our starting, and what it means when delta H does not change, is where we start. So our reactants and where we stop, it does not change when you add a catalyst. The only thing the catalyst will affect is the activation energy or the reaction pathway. All right, so that is our little intro to Unit 6 on 6.1 and 6.2. I'll catch you guys next time for 6.3.